In this video, we're going to learn how to find the vertical asymptotes of a rational function. Now, a rational function in lowest terms will have a vertical asymptote x equals r if r is a real zero of the denominator. In the last lesson, we looked at these zeros as a place where the function was not defined and a hole in its domain. And now we'll see that these oftentimes will be a vertical asymptote, which is a vertical line that the graph follows but never touches. And I'll show you an example how that affects the graph for this first example, and just assume something very similar happens for the other graphs as well. And in a later video, we'll go over how to actually graph these functions. So first, lowest terms just means that there are no common factors between the numerator and the denominator. So for each example, we're going to check first to see if there are any common factors before we decide if there will be a vertical asymptote. And to do this, I'll just have to factor each of these expressions. So I'll look at r of x. The numerator is just x, can't be factored any further, but the denominator is difference of squares and can be factored into x plus 2 times x minus 2. Looking at all the factors, nothing cancels out, so I see that there's no common factor. So each factor of the denominator leads to a vertical asymptote. So I'll see here I have x plus 2 and x minus 2. I'll set them equal to 0. So x plus 2 equals 0, and x minus 2 equals 0. And I'll get x is equal to 2. And x is equal to negative 2. So my vertical asymptotes will be x is equal to negative 2 and x is equal to 2. Now, what does that mean for my graph? Well, at those two x values, I have a vertical line. I'll make a dash because normally you wouldn't see this on this graph, but we'll use it as a guideline so you can see how it affects the graph. Oftentimes when you have an asymptote, it affects the behavior of that graph. This graph in particular, this is what happens with it, is when I approach that spot where negative 2 would be, it kind of curves down and follows it. And then on the other side, as it goes up towards it, it will follow that asymptote, but just get really close and never touch it. And even with the other asymptote, as I approach that value, it just never quite touches that asymptote. Even up here, as you approach it from the other side, it kind of bends and goes up it. So it kind of creates these really dramatic turns and bends within the middle of a rational function. So just imagine this, if we ever have a vertical asymptote, that's what's happening with the graph. It's like a split, like maybe both lines will follow it, but there's a big wall in the middle, and it kind of just smashes into it and follows it as it goes up these lines, or down these lines. Next up we have g of x, which is x squared over x squared plus 1. They shouldn't share any common factors, because up top we have two factors of x, and x is not a common factor between both terms. And this is also not a factorable expression, at least not with any real numbers. So we can't necessarily just go ahead and factor to find them. So just to make sure that there aren't any real zeros of that denominator, I'm just going to set it equal to 0 and solve. And I'll get x squared is equal to negative 1. I'll take the square root and get the absolute value of x is equal to I, which is not a real number. So since the function is only undefined when x is I or negative I, then there are no vertical asymptotes to this graph. So there are no vertical asymptotes. So you won't see a split with this graph. And in fact, its domain is all real numbers as well. Now let's look up here at h of x. Now I'm definitely can factor this. So here h of x would be equal to x squared minus 9 can factor into x plus 3 and x minus 3. And x squared plus 4x minus 21, I'd be looking for two numbers that multiply to negative 21 but add to positive 4. Well, that would be positive 7 and negative 3. So it can factor into x plus 7 times x minus 3. And we'll see here that they do have a common factor. So what I'll do is cancel out that factor, and instead use a simpler form of this function, x plus 3 over x plus 7. One thing to keep in mind with its domain, this is just to help out for later, is that x cannot equal positive 3, which is what x minus 3 would have given you as a 0 for the denominator. So just keep that in mind. But now looking at this, now that these expressions don't share any common factors, I'll set my denominator equal to 0, and I'll get x is equal to negative 7 will be the only vertical asymptote. X equals negative 7. Which means that at x equals negative 7, way down the left over here, with this grid, I would have one of those lines which the graph would approach but never touch. Now look at this next example. We have to try to factor these as well. Now they have a coefficient in front of x squared, so we'll have to use grouping. Meaning we have to find two numbers for the numerator. Look at 2x squared minus 5x minus 12 that multiply to a times c, which would be negative 24, but then add to the middle number, b, which is negative 5. And for my denominator, I'm looking for two numbers that multiply to negative 12, but add to negative 11, that middle number. So for my numerator, those two numbers are going to be negative 8 and positive 3. That multiplies to negative 24, but adds to negative 5. And for my denominator, I'm going to use negative 12 and positive 1, which multiplies to negative 12, but then adds to negative 11. So when I go to factor q of x, I'll write 2x squared minus 8x plus 3x minus 12 all over 3x squared minus 12x plus x. And I just split that middle term to do this. And now I'll use grouping to finish the factoring, which I'll group the first two and the last two terms together and look for a common factor within that group of 2. So what's in common between 2x squared and 8x? Well, that's just 2x. And when I factor that out, I'm left with x minus 4. My second group has a 3 in common, so I can factor out a 3. And I'll be left with x minus 4 as well. In my denominator, 3x squared minus 12x has a 3x in common, so I can factor out a 3x. And I'll be left with x minus 4. And my second group doesn't have anything in common, so I just have x minus 4. Now, both of these groups have an x minus 4 in common, so I can factor that out. So I'll have x minus 4 in my numerator and my denominator, which is a good sign that they have a common factor I can take out. And when I factor those out, I'm left with 2x plus 3 and 3x plus an understood 1. So now I can cancel out those x minus 4s, and my quotient, my rational function, is equal to 2x plus 3 over 3x plus 1, as long as x does not equal a positive 4, which comes from the x minus 4 I canceled out. So setting my denominator equal to 0, 3x plus 1 equal to 0, I can get that x should not equal negative 1/3, which leads to a vertical asymptote at x equals negative 1/3. So the general process for finding these vertical asymptotes is to factor, cancel out any common factors, then just set your denominator equal to 0. And you'll find all the vertical asymptotes that exist for any given rational function. And that is how you find the vertical asymptotes of a rational function.